Good morning. My name is Jyrki Latokartano. I work as a project manager in TRINITY project at Tampere University, who is coordinating the project. This is the last one of this series of Robotics for Industry 4.0 webinars, where our external demonstrators or the third-party companies are presenting their work on the TRINITY topics. Today's session will focus on human-robot collaboration and different applications for that. So please do mute your microphone, and during the presentations, if you want to ask questions, you can place those on the chat window, and then after the 5-minute presentations, there will be 10 minutes for questions and answers, so that the presenters can then answer your questions on the chat window, or you can also raise your hand in Teams and ask for the floor, and then ask your questions during this session. We will have a short introduction to TRINITY project, and then we will have 5 different consortiums from TRINITY Demonstration program presenting their work. TRINITY DIH is a Horizon 2020 funded project, which is now roughly halfway. We still have 2 more full years to go, and the main aim of TRINITY is to improve the agility and innovation potential of the European manufacturing SMEs. And for this, we are building a network of digital innovation hubs who can contribute to the agile manufacturing. And the practical approach we have comes from the use cases and demonstrations, which I'm gonna introduce a little bit later. And then you hear some examples from the 4 or 5 consortiums also presenting this topic today. TRINITY Consortium consists of 16 partners from 10 different European countries. We have universities, research institutes, then we have some companies and also other associations who can support in building our digital innovation hub. And then we have partners who provide us with the digital access point and the third-party funding platform and other needed resources. TRINITY is focusing on agile manufacturing, and we have 3 thematic areas we are focusing on. First of all, of course, robotics as a technical means for providing this strong focus on Internet of Things and other technologies related to Industry 4.0. And then the third one is cybersecurity, which is becoming more and more important also in manufacturing when everything goes to cloud and everything is connected. How do we handle both the safety and the security? The approach in how to support the SMEs and manufacturing companies in TRINITY is quite pragmatic. We are building a critical mass of different examples and demonstrations that the companies can use to find new ideas and improve their manufacturing and their agility. This means we have brought results from previous EU-funded projects, and we are working further on them to provide them as easy-use modules and technologies for SMEs to adopt. So these are the so-called internal use cases, which consist of technical modules, which are openly available for all interested companies. And the idea is that from these modules, they are building blocks where the company can build an agile manufacturing system that suits their needs. And the companies and the consortiums who are presenting today, they are funded from TRINITY Demonstration program. So they are providing their own modules and ideas for all the companies to benefit and get new possibilities how to improve the manufacturing. And then for these we have the open calls, which then lead to these demonstration programs, where the first one has now been running since July this year. And today we're gonna hear from 5 different consortiums in this program what they are working on and what is their progress. We were, I think, quite successful in our first open call. We attracted 115 applications from 27 countries, and those applications presented nearly 300 companies and organizations around Europe. The selection for the consortiums and topics to be funded was made by a group of external evaluators, where we also gathered quite a good group from around Europe, technical specialists, funding specialists, and such, who evaluated the proposals and made the pre-selection, which were then graded, and in the end we were able to fund 19 proposals, which have altogether 44 beneficiaries. So they are consortiums of one company up to 3 companies. They are from 14 different European countries, and the budget we have allocated for these demonstrations was 4.66 million euros. So it was up to 300,000 per consortium. So there's quite a good funding, and we are expecting quite a nice and important results from these demonstrations. And as mentioned, they started in July 2020, and they last from 9 to 12 months, most of them 12 months. So we will see the final results next summer. To be able to support the SMEs and support the consortiums, we have also assigned a mentor from TRINITY Consortium to each of these demonstrations. The idea behind this is when we have new companies who have received EU funding necessarily, or necessarily have not even ever had externally funded research projects. So we can support them with the bureaucracy and other practical matters. Also, as TRINITY aim is to support the manufacturing SMEs, this way we get closer contacts and we can hear directly from the participants that what kind of support is needed, both technically and financially or by business-wise, so that we also learn what kind of services should the TRINITY DIH provide once it is established after the EU project and EU funding is over. So this way we can get a closer collaboration, and so far the results seem quite promising. We have also a second open call coming, and we hope that to attract also a good group of companies. So this is some brand new information not disclosed later or earlier. So basically we will open the second open call in February 2021, and it will be open for about 3.5 months. So you have plenty of time to prepare your applications and build your consortiums. And then we have an evaluation process and negotiations and those. And the aim is that this second demonstration program will start in November 2020. The rules will be similar as in the first call, but the demonstrations will be a little bit shorter, up to 10 months, and the grant will be slightly smaller, 200,000 per consortium. Total budget we can allocate for this is 3.5 million, so there's quite a good money available for interested. We will more emphasize the European dimension in this, so we try to find consortiums from one or more European countries, and then have some preference on those consortiums who can also bring in new countries for the TRINITY network, especially the countries from EU 13 group. And hopefully we can still simplify the application process so that this whole thing will be easier for companies to apply. But for more information on this, you can follow our channels, you can join our emailing list, and in LinkedIn and Twitter we will inform on new activities. From there you also find links to these webinar recordings and other important information. If you are interested in the bigger picture, what's happening in the future of manufacturing in Europe, TRINITY partners are also taking part in the webinar, which is arranged later today, 3:00 p.m. Central European time. So there is a link. You can see if you want to hear a bit on the information on the background. So please register for this one as well. But for today, we are now on the last series of these 4 webinars focusing on human-robot collaboration this time. And as mentioned, these webinars will be recorded. And today's speakers will present 5 different consortiums. And without further delay, let's move to the first one, which is DynaMo, led by Adaptive Robotics in Norway. And this demonstrations is aiming for to simplify robot programming and make robot cells more flexible by using dynamic motion planning. But let's hear what are the ideas behind this demonstration, which will be presented by CEO of Adaptive Robotics, Joachim Paasche. Welcome, Joachim.
Thank you, Jyrki. So, Adaptive Robotics is a spin-off from SINTEF, which is the largest research institute in Scandinavia. Can you hear me well, by the way? Yeah. So, SINTEF is the division within SINTEF working within robotics is the fastest growing division in SINTEF. And based on all the needs that they've seen from the industry, they discovered the need to develop software for dynamic path planning for industrial robots. So you can move on to the next slide, Jyrki. Yeah, so in traditional industry, robots are extremely not intelligent. They basically move in exactly the same path for each cycle. They pick up an object from an exact position and they do the same repetitive move. Now, this works for big companies which are producing millions of units of the same kind. But as soon as there are small changes in the cell or some unpredicted things are happening, the robot will stop working. So in order for robots to be more widely used and in order for them to be applied much more in smaller companies, the thing that needs to happen is that robots really need to become more flexible and they need to be easier to program and set for new tasks. So yeah, if you can move to the next slide. So what we have in Adaptive Robotics and what was developed in SINTEF over a period of 5 years is an algorithm which allows for calculating the global path for an industrial robot arm in milliseconds. So it means that we can basically calculate the optimal path for the robot during robot operation. And we can use any kind of input to our algorithm, such as 3D sensor data, CAD, and so forth, or a combination of the two. The way we achieve our goal of being able to both provide a global path, which is a mathematically complex calculation, and do that so fast is because we're doing an offline pre-processing. So we're building a map of millions of different robot configurations, which is then compressed in a very smart way. And then when we run the algorithm in real time, we're using the offline stored file and using GPU parallelization. Yes, so we can move to the next slide, Jyrki. Yeah, so the key value proposition is that we're capable of providing a reliable, dynamic global path calculated on the fly in milliseconds during robot operation. And it's also very important to emphasize that our technology provides a deterministic approach. So the robot will not get stuck thinking, which is usual for a lot of dynamic path planners. So if you move to the next slide, Jyrki. So this is a demonstration which basically demonstrates a lot of the capabilities. Can you press play? So this is actually a dual arm robot application. So the robot is picking coordinates and where it should go, and the path planner basically takes care of everything. So it calculates the optimal path for both arms, and it also synchronizes to the two arms. So based on continuous replanning, so it provides optimal dual arm capabilities. And here you can see that first it picks, there are only two pieces that are available without collision. And when they are picked, then the others becomes available. So this is a very practical and nice tool. So what we're basically accomplishing, if you move to the next slide, Jyrki, is that there's less development time and faster deployment, because you don't need to think about the movement for the robot. You don't need to program any waypoints. There's less code and much more elegant code. If there are changes in the cell, the dynamic path planner will dynamically adapt to it. And we also provide lower cycle times because we provide optimal paths. And also in this case, as you saw, much more optimal dual arm operation. So if you move to the next slide, please. So we see that this technology can be used in many different types of robot application. The key kind of thing to mention here is that it has a value in cases where the robot is picking from multiple different positions for every cycle. So when the robot has a unique cycle path for each cycle, in case like bin picking and multiple arms, palletizing, and also of course human-robot collaborative applications. So if you move on to the next slide, Jyrki. Yeah, so we will provide our product as an SDK, so people can build that into the robot application, and they just need to provide our algorithm with some input, basically robot, gripper, CAD, point cloud, so forth, and then they just ask for a path, and we provide it. So that's how we see the product. Yes, you can move on to the next slide. So we're a very neat and very agile team for the moment. So everybody's working 150%, and this is the team you're seeing. And it's a very good collaborative environment. And we're constantly in the process of trying to develop the first industrialized solution for our technology. Thank you.
Thank you very much, Joachim. Any questions? So far. So basically, this is a product or technology you've been working for quite some time. What are the main things you are focusing on TRINITY project?
Yes, so we're developing and testing it as part of a bin picking application together with KUKA. So it's really testing and benchmarking the increased performance in terms of less code, lower cycle time, and also robustness of our technology. So we need to demonstrate that it can work over a longer period of time. So that is basically the main focus of the project.
Okay, so this one you are working with KUKA robots, but do you have any limitations concerning the robot brand, or would this technology work basically with any controller?
Yeah, so we can work with any robot, in essence. So as you saw in the demonstration, it was a dual arm with robot with 2 7-axis. So that's kind of the more complicated. But we can work with any robot type.
Okay, good. Any other questions to Joachim? Okay, if not, you can find more information from the Adaptive Robotics web pages, and also in the TRINITY web pages you get the contact information and those if you find this interesting, so you can be in contact with Adaptive Robotics if this would be something that you could utilize in your own production. But thank you, Joachim. We can move on to the next presentation.
Okay, good morning. I'm Paulo from AllbeSmart.
Good morning, Paulo. So basically, the Agile project, which will be next presented, will present possibilities to improve the agility and productivity of the automotive cable production, which is a very manual and quite labor intensive phase. And on this demonstration, Paulo and the team is working on finding some robotic solutions for this. But I give the screen to you. Go ahead.
Yes, please. So if I can share the screen. Okay, so
I think you should be able to take it, share it from there. I can stop sharing. So
can you see the screen now?
yes, go ahead.
Good.
Now we see the whole PowerPoint, not the presenter mode, but.
And now you can see
now
the
presenter. Now we see the whole slide. Yes, go ahead.
Okay, so good morning, everybody. So my name is Paulo Marques. I'm the founder of AllbeSmart, and together with the other company, a manufacturer company, Stone Shield, we are working in this experiment called AGILE. So the main goal is to increase the agility of the automotive cable assembly industry using TRINITY Robotics solutions. So we are based in Portugal, and we are a consortium of 2 SMEs. AllbeSmart is more technology oriented, let's say, as an engineering research and development company, and Stone Shield is a manufacturer industrial company that provides machines for the automotive cable assembly industry. So this is our target market, so is the wire harnesses. So in fact, 60% of the cables, electric cables that are produced in the world are are included inside the cars. So cars has a lot of wires that needs to be produced in efficient mode, and there is a significant manual work in this process. Is why most of the factories are located in cost-effective labor countries like India and Mexico, and quite far from our location. So the idea here is to contribute to the automatize the process and sell machines for the companies that produce the wires to the cars. So the background is that more than 90 million vehicles are manufactured every year. 60% of the electric cables manufactured are installed in cars. Car manufacturers are using increasingly smaller components. So this miniaturization process is quite challenging for the manual process. So automation increases production, reduces costs, and ensures quality. So there is a demand on the market to automatize some of this process. And this requires, of course, training of the people that use the machines, and also specialized maintenance operations on the field. So we see a market opportunity here because the complexity and diversity of the assembly process that needs to be automatized to replace this meticulous manual work requires state-of-the-art robotics, computer vision, IoT, artificial intelligence technologies. So these are all topics that are addressed by the TRINITY project. And the upcoming trend of electric and self-driving cars requires new electric components that needs to be produced, and they will need new machines to produce these components. So there is here also an opportunity to design machines able to produce these new components. And this market scalability here, because the same machine can be sold to many clients. In fact, regardless the brand, all the brands needs the same kind of cables. So there is here a market that we can address in the scalable way. So this is our position in terms of automotive value chain. So AllbeSmart is a technology provider. So we work with machine vision, augmented reality, IoT, and artificial intelligence. So we are more, let's say, a software company, and we provide technology to Stoneshield, that is an industrial company. So these two companies, this is a consortium from TRINITY. We get expert TRINITY in collaborative robotics, AI, artificial intelligence, mentorship and funding. So this will feed our consortium, and then we produce machines for the cable manufacturers. These are big cable manufacturers that then sell the cables to be assembled inside the automakers, okay, big automakers. So we are here in the, let's say, in the third layer of the automotive value chain. So the main objective of this demonstration is to seek TRINITY support in the improvement of the next generation robotic machines produced by Stoneshield for the automotive cable assembly industry. So actually we are addressing 3 use cases with 3 demonstrators. So the AGILE Demonstrator 1 is the objective is to increase safety and speed of human-robot collaboration process in the cable assembly industry. Demonstrator 2 is using augmented reality based application for the training on the job of a cable assembly machine operator. And demonstration 3 is the use of artificial intelligence vision system for classification of different cable connectors and pick up by a robotic arm. So for these 3 demonstrations, we are aligned with the 3 use cases from TRINITY. So the TRINITY use case 1 on collaborative assembly with vision-based safety system. Here our mentor is at Tampere University for AGILE Demonstrator 1. So we want to reuse some of the ideas of this TRINITY use case in our application scenario. TRINITY use case 10 is related with our demonstrator number 2 because it's related with augmented reality for training operators. And the TRINITY use case 17 that is on artificial intelligence vision for pick and place robotic arm is related with the AGILE Demonstrator 3. So we have 3 mentors and 3 demonstrators. Okay, so let's go more detail on demonstrator 1. The idea is to increase the safety and speed of human-robot collaboration in the cable assembly industry. So we'll demonstrate a vision-based safety system where a dynamic map of the working environment, robot components and humans is continuously updated. The robot working zone is projected onto a flat surface, and the robot and the workers function as members of the same assembly team. So we can see here in this picture, the robot and the human operator are working together in the assembly of the fuse box. This is a fuse box used inside our cars, needs to be assembled. Currently, this process is manual. There are some fuses that are very small that we believe they can be optimize if you use robotic arm. So you have here a collaborative robotic scenario, but the topic here is also on the safety line. So here safety line is projected by the projector and is adapted, depends on the kind of the box that we have. So this was inspired on the Trinity use case 1. Okay, so we are going to reuse some of the ideas, and we are in contact with Tampere University. So addressing this. So in the Agile Demonstrator 1, okay, again, so here is the place for the operator, and you can see that the project safety line is projected, and with this we can contribute to the safety of the process and also to speed up the process. So the idea here in terms of key performance indicator is to reach 30% decrease in the cycle time of a fuse box assembly process and optimize the trajectory planning also. So in Agile Demonstrator 2, this is related with augmented reality. We will demonstrate an augmented reality application for industry that will provide step-by-step tutorials, step-by-step instructions for maintenance operations that are facilitated to access to IoT information from the machine, so sensors, and remote assistance support. This is very important because these machines that StoneShield produce are used, as I told you, in countries like India, Morocco, China, so across the world. And not always there exist competent people there to do the maintenance of the machine. So in order to avoid costs to send people to the factory to do updates on the machine and maintenance, it's very important to have a more a smart way to do this using augmented reality. We will design an application able to provide maintenance instructions, training, documents, alerts from the machine, and also remote support. So here we are working with the Unity framework now for this specific machine. You see and we are also developing the remote support to help people that is on the field. So we plan to decrease the cost of average time required for training and maintenance and 50%. Okay, here the Agile Demonstrator number 3. This is related with the use of artificial intelligence for a vision system for classification of small plastic components and pick up by a robotic arm. So the objective is to increase the speed and reliability of this process. We are using object classification and object detection using deep convolutional neural networks. And our mentor here is Janis Arends from the Institute of Electronics and Computer Science in Riga. We are sharing ideas, and we are going to reuse some of the code they have produced to speed up this process. So the idea is you have this kind of connectors that are inside boxes, but in the random way, different kind of connectors, and we have to sort these connectors. So we have unsorted small components, an open tray, a bin picking process that are sorted based on the kind of connectors. So again, we are going to use an OMROM TM5900 to do this process based on artificial intelligence and decrease the average cycle time to seconds. Okay, in terms of timeline, you are here in October. We already report level 2.1 with a detailed explanation of the AGILE experiment, and we are in contact with our mentors to get feedback. And this is the timeline. So we are now currently more focused in the design of the augmented reality application, and in use case 3 on this bin picking process. So we are more focused in these two application scenarios, and we count to have to have an intermediate progress report in December, where we'll have already some initial results. Okay, this is all. Thank you. Have any question, please?
Thank you very much, Paulo. Are there any questions? So I think it's quite an interesting project because it has many of the Trinity modules in testing. So it's we are quite eager to learn that what has been developed in these projects, the ideas, are they applicable in the industry? So I hope this will be quite fruitful both ways, that we learn more what to focus on and what kind of features are needed, and hopefully then in your systems and production you will find new solutions for the production problems. But at this point, how does it seem to you? Does it require quite a lot of work or not so much work to make this really usable in industry, because they are after all research project results, so they are not ready products yet?
Yeah, we see here for sure the augmented reality application is an urgent need of the company. So I would say that more close to the market is the augmented reality application scenario. The collaborative robotics, okay, is a way to increase the speed and the process, but let's say is more on the research side of the company. But for sure, the augmented reality is something that is very important, because as I told you, these machines are in remote places, and we spend a lot of money sending people there, sometimes to solve small problems that could be done remotely with support from the air.
Yes, I think that's definitely something that can be used in many different industries, and that's probably is the closest one to the market, or some solutions already exist. But happy to work with you and also get some insights on how to develop these modules and use cases further, so that they would be going into the direction that the industry would really benefit from them, so that they are not only some academic research results that don't interest anyone. So I think hope we have a very fruitful collaboration here.
Okay, thank you. We'll give our best. Thank
Any
you.
other questions? Not at the moment. So you have Paulo's contact there on the screen, so you can be in contact later. Also, there was a question earlier for the previous presenter about adaptive robotics link, so you can check the chat and maybe answer there if you have some more detailed link. But now let's move forward to the next presentation, which will be the AMS Affective Manufacturing System by the consortium of Mentec and Tegema. And this project demonstrates a production platform with for high quality production with low volume and high mix operation.
My name is Reon Smits. I'm the CTO of Mentec, and I will be presenting today. So we are currently developing an effective manufacturing system, which is a system that takes the stress or emotional levels of an operator into account. And we want to, with this Trinity project, we want to demonstrate the relation between stress or the emotional levels of the operator and the yield of the production process. We do this together with Tegema. Maybe it's good to give a first bit introduction of the company. So Mentec develops mostly systems or products to detect emotions and stress levels at people. Until now, we did it mostly in healthcare, but we have a strong relation with the high-tech sector, the manufacturing sector. And therefore, we set up a partnership with Tegema, and Tegema is a company also located in the Netherlands. and they make high-tech systems for fine alignment and curing of mostly photonic products. And together we have defined this project to see if in high mix products where there's a high risk of errors with a high cost, if there's an error, if we can measure there the performance to enhance the yield of the system. Okay, let's go to the next slide. So in cyber-physical systems, there are generally 3 performance indicators. So you have the yield or productivity of the system, and you have the quality of the product, and you have the operator arousal or satisfaction with respect to working conditions. And this, the performance of this process depends on the complexity of tasks and the arousal level of the operator. And for example, with a difficult task, you need a high concentration level, and if you have to do that for an increased amount of time, it can generate, it can lead to errors because of the loss of focus. With the simple tasks, the reverse is active, so you have a simple task which is very repetitive. You don't have to think much about it, and when you which will also create a loss of concentration and can also introduce errors. So in this project we have in general 4 objectives. So the first objective is to demonstrate a smart factory concept, where we take this stress detection and emotion detection into to optimize the production. The second objective is the demonstration of a Siemens streaming software platform, where we can use our AI algorithms in real time, and also add control features such as process monitoring and other environmental factors into the equation. The third objective is to demonstrate a use case where we can assess the operator stress. For example, there's too high stress or too low stress, and we can include it in the decision tree to enhance safety and to optimize production performance. And then the fourth objective is to build an appealing showcase. So that would be the deliverable at the end of this project, where we can demonstrate the effectiveness of the human factors into this process equation. Okay, so what we have developed in the past years is the HUME. The HUME is a system that uses physiological parameters such as heart rate, skin conductance, acceleration, and skin temperature. It can we collect those parameters in real time via existing wearables over Bluetooth, and that data is analyzed real time in a software platform. That software platform uses AI to find correlations or patterns between those parameters and a certain stress or emotional level. To get that data, we have a lab where we typically do tests. So what you see here on the picture is a guy that's watching a VR movie or a VR game where there is a stress impulse. That stress impulse we measure with physiological data. So we use EEG, we use the MoveSense, which is a spin-off of Suunto. We use Empatica, which is an MIT spin-off. We use cameras with infrared, we use microphones, and we use EMG. And that data is used to as a ground truth to build our models with. Of course, there are different environments where you can have that. So you can be sitting still, you can be standing, you can be walking, you can do different activities, and all those activities also influence the way the model works. So we define the 5 tests where we can measure the data and build models in different environments or different situations. And that data is analyzed by humans. So we have behavioral experts, behavioral scientists that assess the data, and then based on that assessment, we train our models. Where this is one of the results where you can see that in blue the depiction of the model is given, and in red and black the observations of a professional, where you can see that we are quite accurate in detecting stress or no stress. We have so of course we do this in multiple times. So in total we now have 125 people in the database, and we train those models on all those people, and that gives a general view of the precision and the accuracy of those models, which is shown here, and it shows that we have the accuracy is increasing as the models advance. And we're now around 80–90% accuracy on detecting stress in a controlled environment. Next to physiological parameters, we're also looking into face recognition. Of course, there has been a lot done with facial recognition, but we think in a static setting where an operator is behind a machine, where you can expect him to be at a certain position, you can also easily use facial recognition, which gives us a lot of opportunities to also create a better image or a better indication of stress or a certain emotion based on facial recognition in combination with our existing models on physiological parameters. So we define this project in a stepwise approach. So we define two stages. The first stage is to demonstrate the relation of operator stress with a pick-to-light system. So that's a very simple way where we can assemble a product, have a certain amount of steps, and for example, introduce stressful factors such as decreasing time to assemble the part, or different parts or different versions of the part with slight alterations that encourage you to pay attention and don't do the wrong thing, but which will end up in a disapproved product. And there are more factors that we can increase. For example, introduce badly made products or badly made parts that for the product that do not fit correctly, or that cause a lot of stress for the operator. In which we can show the relation between our existing models based on the physiological parameters and the facial recognition I showed earlier, and the process that we have, and demonstrate that we can measure the stress that this generates at an operator, that we can measure that. Stage 2, we want to also introduce some automation. So we want to let the operator work together with a robot. We have a partnership with ABB, where we will use a robot to assemble the part of the product, where the robot is depending on the operator to supply the part on time. And there's interaction between an automated system and the operator. So the automated system can use the feedback from the system to, for example, change the way it cooperates by taking another step of the operator when he's taking more time to assemble the product. So we define the use case for this. So the total use case is where we pick and assemble parts. That will be the pick-to-light system, the first square you see here. Then we have to, it's a photonic product, so we also have to do some alignment and curing. So we align the product on the base with a robot that will cure it, and then the operator can finish the product by connecting the housing with screws and mount the cover on it. For that, we now have built the first pick-to-light system, where we build an HMI interface and some very simple assembly process based on Lego. But we can also already introduce that product. And in the end, it's the idea that this will be integrated into a nicely built system, like a machine, where this is integrated. And that is my story for now. This is what we did until now, and if there are any questions, I'm happy to answer them. Thank you very much.
Thank you very much, Rian, for the presentation. Quite an interesting topic, bit different from the others, but definitely something quite useful. Any questions? I believe this is something that will become more and more important when or if the human-robot collaboration will really move into the industry, in the sense that the human and robot are really collaborating at the same time, not only here and then, so that all these systems, of course, need to be designed in the way that the human is defining the pace, not the machine. And I think this kind of a system would be quite valuable, so that you can slow down if it seems that the human gets too stressed and starts to make mistakes, and then of course that can ruin the production. So I believe there's also quite a lot of usage for this kind of system in industry and also other areas. Any questions on this topic? There was a comment about a nice presentation, but not a separate question. It was interesting. So
yes, thank you very much. Yeah.
You're welcome. So here you have Rian Smith, and then the main contact for this demonstration is Erwin Minders. So you can contact, I believe, both of them and follow the progress of this demonstration also in the TRINITY web pages. But let's move on. The next demonstration is called Trainman Magos, and it's by Quanta and Qualia in Greece, who are investigating the use of Magos glove in programming robots and improving human-robot collaboration. I believe Greg Agriopoulos will be presenting.
Yeah. Hi, Jyrki. Thanks for the floor. Let me share my presentation.
Yes.
Okay. Can you see my screen now?
Yes. Now we have PowerPoint and.
Yeah. All right.
Yes. Go ahead.
All right. Thank you very much. Our project is called Trainman Magos. We're analyzing use case number 15. The problem we have identified is that current state-of-the-art solutions, in order to enable and increase the automated solutions for industrial robots offering high dexterity, needs a new approach, and the programming procedure is too complex. When articulated finger and hand motions are required during programming robots. So our approach here is to apply a new technology and demonstrate its usability in the industrial and robotics sector. So potential users are with manufacturing industry. The focus now is on automotive and aerospace, but the experiment may be more widespread in other areas as well. The brief description is that we introduce a new and very accurate technology, very data reliable technology, in order to collect data from human hand motion and apply them to a hand robot and a robotic arm in order to perform exactly the same movements. We're involving Magos gloves and robotic systems with an arm robot and a gripper. The partners in this consortium is Quanta and Qualia from Greece and CTAG from Spain. Our possible benefits and our goals is to increase the productivity for technology adopters following demonstration experiments by decreasing the complexity of trajectories programming time, and the goal is to reduce that time by 20% or more if possible within the experiment, and increase the production, the company production and the industrial production due to actions by decreasing the complexity for programming robots to perform high dexterity tasks. In the low picture, you can see the Magos prototype and in lab, let's say, photo demonstrating the indoor localization system and the glove. And in the upper photo, you may see the interaction scenario we're applying in this project. So our solution is split by two parts. The first one part is based on Magos platform. So we initiate the indoor tracking system, and then a worker wears the Magos gloves and performs the tasks. Here we need to point out that the technology collecting and analyzing finger-hand data is a patent-pending technology with very data reliable and accurate characteristics. Like we track 22 points on the hand, mainly the finger joints. So 22 degrees of freedom with accuracy 1/15 of degree. So it's a very accurate system to depict the data that the human hand performs. And of course, it's wireless, let's say, interconnected to a PC. So we collect the data from a specific task performed by a worker, and then we analyze the data in a local computer. Of course, after that, we select the robot models. As I said, it's a robotic arm and a gripper. And the computer calculates robot motions and selects appropriate control in order to perform the exact same tasks with a robot this time. And then a quality control is performed on the final, let's say, result. Here is the technical architecture of the system. Right now, in the glove, we already implemented a finger and hand tracking system with hand orientation and then the indoor localization system that will give us the exact data where the human hand and the human fingers are. And also we have applied pressure sensors in order to sense the force that the operator puts on in order to provide this data for the robot. So we collect all this data to the high-level control system where we analyze the data and extract the desired path depending on the robot side. And then in the low-level control, depending, of course, in the robot and in the gripper in particularly, we perform compliance control and we drive robots actuators in order to perform the exact same tasks. For this experiment, we have fixed the use of KUKA IWA robot for the location of the hand, let's say, and then a gripper attached to the robot in order to perform the specific tasks. The gripper we have selected is a gripper by robotic with 3 fingers, and the task is to grab a glass door, and insert and manipulate it in order to be fed into a car door, for example, a task that right now is only performed by humans because the programming of robots in such articulated and texturous task is not possible at the moment. Of course, our plan is to start with some non-so-fragile components, for example, some plastic components, and then move on smoothly to a glass, let's say, object, and keep on improving the performance and the data collected and processed in order to feed the robots. The leading partner of this consortium is Quanta & Qualia from Greece. We are a deep tech startup developing Magos product. We envision of a future where current human-computer interaction devices will be replaced by more intuitive ones, and we have developed a very, very innovative technology that could be implemented in many sectors and in robotics as well. We're a team of 10 professionals with backgrounds in robotics, extended reality, hardware and software development, 3D printing and design. And our office is in Athens, Greece. Our partner, CTAG, is a Spanish private non-profit R&D technology center devoted to support the automotive industry in research and development and innovation needs. CTAG was created in 2002 thanks to a joint initiative of automotive enterprises within the region. CTAG is present in all the stages from analysis, validation, and verification to implementation at client sites and product improvement. They work with main OEMs and TRs, mainly in Europe, in main 4 activities: production and process development, testing and validation, passive safety, and electronics. In this project, CTAG will carry out the implementation of the robot equipped with the gripper. So this is our consortium. Our mentors are Patras LMS Laboratory and Sotiris Alvaliotis in general. You can see the social media, let's say, links, and I have a short video to demonstrate to you. So right now, the stage we are, we have performed some in-lab tests wearing the Magos system and grabbing some virtual objects in a virtual reality environment, something like the system you see. Of course, we collect the data by performing some very complex tasks for grabbing objects in a virtual reality environment. And in parallel, we have provided the data to CTAG in order to incorporate them in a simulation environment for the Kukai IWA robot to perform at first the indoor localization, let's say, match with the robot and test if the data are correct. And we see a lot of match movements between the hand and the robot. The next step is to right now we are analyzing the finger and hand orientation data, and we will move on with the pressure data applied in order to check the final result and in the very end perform the demonstration in CTAG premises. So thank you very much. That's all from me.
Thank you very much for the presentation. So are there any questions to Greg? I think this is quite interesting demonstration in the sense that the same technology can also be used with service robotics and those kind of applications. So I think it's not only for the industry, but I think it has a good potential also elsewhere.
Thank you very much, Jyrki.
Any other questions? Doesn't seem to be anything on the chat window, so we'll thank you, Greg, once more. And the contacts are there, so you can ask further questions. And also we will, of course, have this whole webinar recording available. And then there will be some additional information in the Trinity channels as well. So let's move to the last presentation of today, which will be given by Stefano Ellero from STAM in Italy, and their demonstration is called ICON, and they are working on getting a robotization of the manual coil winding, so how collaborative robotics could help in this also very manual and laborious task. Go ahead, Stefano.
Okay, good. Thank you, Jyrki. Can you see my presentation?
Yes.
Okay, great. Then let me open the presentation mode. Okay, here we go. So yes, as Jyrki correctly pointed out, our project starts from a real industrial problem that is at the base of our experiment. And this is that small manufacturers of electric motors, such as our Romanian partner ICPE, mainly rely on manual work for stator winding. And this is because they usually produce very different motors, but in small quantities. And if they want to increase the precision and the productivity of their product, their process, automatic systems are usually not really fitted for high product variability. And this is where we step in, we can say, and that's why we have developed a robotic cell for stator winding, because it is a flexible way, but precise and repeatable to wind these coils without forcing operators to perform like stressing and repetitive jobs. So in the current system layout, the wire of the coils is provided and tensioned by a feeding system, and the robot winds it on a stator. We have installed a rotary table that places the stator so that the pole is in optimal position with respect to the robot. And the trajectories on the robot are generated based on parameters that are input by the operator on an HMI. Since this is an industrial robotic cell, the operator, for safety reasons, cannot enter the working area of the robot. It is something that is currently, let's say, prevented by fences. And the idea at the base of ICON is to make the cell more productive, and that is why we want the operator to perform all the loading and unloading, wire cutting, and so on operations on the stator, while the robot is winding a second stator. And basically, this is why we applied for TRINITY, and we would like basically to demonstrate 3 modules developed by TRINITY partners in order to make our robotic cell more compatible for human-robot collaboration. So we cannot say that it will become a real collaborative cell because we don't have a lightweight arm and a lot of other safety features, but we are trying to, let's say, increase this level of HRC. So safety will be ensured by a laser scanner, and this will be position and slowing down or stopping the robot accordingly. And this will be done by a first module that we are right now applying to our cell. Then secondly, through a projection system, we will provide the operator with information about the winding cycle, the progress buttons also. And besides, the robot envelope will be projected on the working table of the operator. And this is again for safety reasons, in order for him or for her to see where the robot is actually moving, and of course avoid any collisions. Finally, we will use another module, a machine learning module, to double check that the stator that has just been loaded on the rotary table corresponds or matches with the stator, with the parameters of the stator that have been input by the operator. So this will be basically double checking to prevent again collisions of the robot against the stator being wound or any other possible error during the manufacturing process. And thanks to these 3 modules, so we can say thanks to the TRINITY project, we are aiming at reducing the number of defected products, defected windings on our stators. And we are seeking an increase of productivity, because the operator will be able to load and unload the stators and perform all the necessary operations on one stator while the robot is working on another one. So basically we are kind of parallelizing the operations or at least trying to optimize them. And this is possible for us thanks to these 3 modules that we are demonstrating, and therefore we hope that we will manage to achieve these results in order to make our robotic solution even more interesting for industry. And this is basically it about ICON.
Thank you very much, Stefano, for the presentation. I think it's a good example of the approach that you don't always need to go for a collaborative robot, because the standard industrial robots also nowadays have quite nice safety features, and you can do a lot of things with them as well. But any questions on this approach? I think definitely something that should interest the industry working on these coiling issues, because there's quite a lot of electric motors being produced around the world, and a lot of coiling needs to be done either with.
It's also particularly relevant for the electrification of transports, especially for electric scooters and cars, because they have motor layout for traction that are fitted for our cell. So we hopefully will get the interest of the industry for this.
Good. Any other questions? You can raise your hand or write your questions to the chat window. Okay, so thank you very much, Stefano. Thank you very much, all the presenters of today's webinar. So this now concludes our series of the 4 webinars, and hopefully we will have new ones coming probably next spring, when the demonstrations advance, and we can hopefully bring some new news, hopefully also able to actually at some point organize a real physical event, so that there could be also the coffee and discussions and creating the new connections, which is pretty difficult when we do these kind of applications or webinars online. So this is not the best way for this. There is a question for Stefano. When is the return of investment if manufacturers use it?
Well, when is the payback period is somewhere after 12 months, even assuming that the increased productivity of the cell is not completely exploited, meaning that the industry will be able to produce many starters more, but they will be, let's say, somehow stopped by their commercial capacity to actually distribute, to actually sell this product. But if we are talking about the return on investment in terms of the efficiency of the investment, it is somewhere between 20 and 30%, because I mean, the benchmark is the manual labor, which, as we know, it's unfortunately not really super high ROI investment. So I think that is the goal that we have in mind with the preliminary business plan that we have elaborated.
Okay, thank you very much. I hope that answered the questions. So once more, thank you very much for all the presenters of today's seminar. The recording of this one, and as well all other webinars, will be available in YouTube shortly after. There's the QR code you can scan to get to this recording. or then you can also use the link I just posted on the chat window. So thank you very much everyone for participating in this webinar series. Would you now have any questions on today's topic or on these open calls, or maybe the coming open call? Apparently not. So once more, thank you very much for joining us, and I hope to hear and see you later again in the events organized by the TRINITY Consortium. Thank you and have a nice day.